Okay, so in the last video we were taking a look at moments of inertia, and in this one we're going to go ahead and take a look at the physical pendulum. But before we do that, it'll be convenient to introduce the idea of the radius of gyration. Basically, we'll say we have some arbitrary object like that, and let's say this is our rotation axis coming out of the page like so. What we do is we let k be such that, and k is our radius of gyration, be such that I is equal to mk squared. So the idea is that this is telling us what radius hoop we would need to have the same, of the same mass, that we would need to have the same moment of inertia as the object under consideration. A lot of books use that in their tables, and it's just a handy thing to have. Okay, so if that is foreground, let's go ahead and take a look at the physical pendulum. Okay, so let's go ahead and draw up our system here. So let's say we are attached about some point O, and we've got just some arbitrary blob like so. Let's say this is our CM right here, and our distance between those two is L. We'll let the angle be theta. We'll have force of gravity acting here. We'd also have a reaction force from the pin here, but that isn't going to matter. Looking to the future, I'm going to cryptically draw another point here, O prime, and note this distance L prime, mostly just because I want to copy and paste this image. So our axis of rotation here is coming sort of out of the page, so I'll try to do my best to draw it in 3D. All right. So with that, we can go ahead and say that the torque will be, a restoring torque will be equal to minus mgl sine theta. And by Newton's law applied to rotations, that's equal to I theta double dot. So we can put this into standard form, theta double dot plus mgl over I sine theta equals 0. If we pinky swear that theta is equal to small, then we can let sine of theta be approximately theta. And then this becomes theta double dot plus mgl over I times theta equals 0. And we recognize this, and this is omega squared. But to avoid confusion with angular rotations that we've been dealing with, I'm going to call this 2 pi f naught squared, just to keep it straight. This is also 2 pi f naught squared, but a little tougher to handle, but we'll get to it. So as long as we're keeping our angle small, we've seen this before, back when we studied simple harmonic motion, we know the answer. Theta is equal to some theta naught, our amplitude, times the cosine of 2 pi f naught t minus some arbitrary phase delta. And we can find our frequency. We know that 2 pi f naught squared equals mgl over I. So then that means that f naught is equal to 1 over 2 pi root mgl over I. So the period's 1 over the frequency. So that'll equal 2 pi times root I over mgl. And here's where the radius of gyration comes in kind of handy. We can rewrite that as 2 pi. We can express our moment of inertia as mk squared. So then this becomes mgl, right? And we can cancel our m's. And so we get that it is 2 pi root k squared over gl. So this is where radius of gyration is kind of a handy way to express it. It helps to show the mass independence of the period better than the moment of inertia would. Now, we know deep in our heart of hearts the moment of inertia has the mass buried in it, so we know it would cancel out, but this radius of gyration approach makes it more explicit. So let's go and do a hoop. So there's our vertical axis, and our hoop has swung over some angle theta, like so. And the hoop is fixed about its diameter right there. So we can get the moment of inertia from the parallel axis there will be equal to ICM plus mr squared, but the moment of inertia of a hoop is just mr squared. And we can equate that to mk squared if we want. So you get that the radius of gyration of a hoop about the end is equal to root 2r. Well, that's kind of interesting. That means that swinging a hoop about a point on its diameter is just as hard as swinging a hoop that's root 2 bigger about its center. Anyway, we can go ahead and put that in to get the period. That's equal to 2 pi, and then our k squared is just 2r squared over gr. And we can cancel. And so we are left with the period being 2 root 2 pi root r over g. So the period winds up being root 2 longer than it would for the corresponding simple pendulum. All right, so that's all well and good, as long as we pinky swear that our angle is kept small. But what if it's not? Well, in that case, we're going to have to delve into the world of elliptic integrals. For the grins, let's go ahead and find our period the hard way. So let's say this is my object here. There's the CM there, distance L. And we'll say that this is versus the corresponding height at equilibrium. We'll say it's at some height h. So then the energy conservation will be 1/2 I theta dot squared plus mgh equals E. So 1/2 I theta dot squared equals, well, plus, h is going to be equal to mgl times 1 minus cos theta. We've worked that before. And we can get our total mechanical energy by looking at the point of maximum swing. That'd be mgl times 1. Here, let's move the whole thing. mgl times 1 minus cos theta naught. All right. So then 1/2 I theta dot squared equals MGL times cosine theta minus cosine theta naught after we cancel those MGLs right there. All right, so ultimately we can express theta dot, which we'll note is d theta dt on our way to integrating this, is root 2 mgl over I times cosine theta minus cosine theta naught. So we'll separate variables. So on the one side we'll get dt, and on the other side we will get, pulling out all the constants we can, root I over 2, mgl times d theta over the square root of cosine theta minus cosine theta naught. All right, so integrating the left-hand side from 0 to t is just going to give us t. And then for the right-hand side, we're kind of stuck. We're going to get a I over root I over 2. Why do I keep making that pi? Over 2 mgl. And then we're just going to integrate from 0 to theta, d theta over root cosine theta minus cosine theta naught. Now, if we wanted to get the period, a trick we can realize is that if we integrate from 0 to theta naught, that would be a quarter of the period. So the whole period will be equal to 4 times that. I over 2 mgl integral 0 to theta naught, same integrand. Okay, so the total period will be the same thing with a 4 in front and integrating 0 to theta naught. Now these integrands have names, and they are, but we'll get to that in a second. Let's just hold for one brief precious moment just to show that the result is the same as we had before. Let's let theta equal small one more time. If that's the case, then the cosine of theta is approximately 1 minus theta squared over 2. And we have to assume that both theta and theta naught are small here. So then I can get the period to be 4 times root I over 2 mgl integral 0 to theta naught d theta over the square root of theta naught squared over 2 minus theta squared over 2 after I substitute in. All right, that integral we actually know it's equal to pi over root 2 if you look it up in a table. So 4 root I over 2 mgl, and that integral works out to be pi over root 2. So, yay! We end up with the same 2 pi root I over mgl that we had before, just to show that this technique is valid. All right, but now let's go ahead and say that theta naught isn't small. Or well, theta might be small at some instant, but the key issue is theta naught is unequal to small. Well, in that case, this approximation here goes right out the window. And so then these integrals here, let's call them star and double star, cannot be evaluated analytically. So we'll go and put this into the standard form that you see in the tables. So in order to put star into standard form, we'll let the sine of phi, the sine of phi equal the sine of theta over 2 over the sine of theta naught over 2. And we can rewrite that as 1 over k sine theta over 2. So we're just letting k equal the sine of theta naught over 2. So remembering our trig identities then, that gives us that the cosine of theta equals 1 minus 2 sine squared of theta over 2. Alright, so with all of that we can rewrite our integral star. And we get t equals root I over 2 mgl integral 0 to theta d theta over root 1 minus 2 sine squared theta over 2 minus 1 minus 2 sine squared theta naught over 2. Alright, once again, conveniently, at least the ones cancel. That's something. So we can rearrange this a bit. So this will be equal to that root integral 0 to theta d theta over, this becomes root 2 times sine squared theta naught over 2 minus sine squared of theta over 2. Alrighty then. So remembering our integral of the derivative of sine is cosine, so remembering our sine phi, if we differentiate that, our cosine phi d phi, which we get from just differentiating sine phi with respect to phi, is going to be equal to 1 over 2k times the cosine of theta over 2 d theta. Alright, so you go ahead and but the cosine of phi is the same thing as cosine of theta over 2, so we get that d phi is equal to 1 over 2k d theta, and that's going to allow us to make a transformation of variables. So ultimately we get, skipping a few steps here, root I over mgl integral 0 to phi now d phi over root 1 minus k squared sine squared phi. Alright, we'll call this star prime. And similarly, you can show that the period will be 4 times root I over mgl. And the phi is going to, in this case, will work out to be pi over 2. So this will be integral 0 to pi over 2, same integrand. We'll call that double star prime. Okay, now you can't evaluate these analytically, but they can be done numerically. These integrals, we don't care about the root in front. This integral here is called an incomplete elliptic integral of the first kind. Yes, that implies the existence of a second kind and also of a complete one. We won't see the second kind, but we will see the complete in just a moment. Anyway, this incomplete elliptic integral of the first kind usually gets noted as f of k and phi. This integral here is the complete elliptic integral of the first kind, and you either write as f of k and pi over 2, or it also gets written as k of k. You can find these in tables, or you can invoke them in Mathematica. In Mathematica, this gets called elliptic f, and this gets called elliptic k. So, extending further, our period is equal to 2 pi root I over mgl, or I should say our t naught. That's for the simple, if the angle is small. So our actual period works out to be 2 over pi t naught times f of k of pi over 2, or if you prefer k of k. And we can plot this, so let's fire up Mathematica. Alright, so let's make our t naught equal to 1. And then we'll go ahead and plot 2 over pi times our t naught. Then we need the complete elliptic integral, so elliptic k of k, and we can run k from 0, so no amplitude at all, to 1 max amp. Alright, and it looks something like that. So you can see here at small angle, so we get the small angles, but as we go out, we eventually get to double. Alright, to give maybe a little more context to it, let's just go ahead and plot it out as an angle. So we can instead plot, again, 2 over pi t naught. Yep, t naught. So again, elliptic k of, now we'll write as sine of theta naught over 2. And we'll run theta naught from 0 to pi. Alright, so what we get is, if we pull it all, that it diverges. And you can see, so if we stand perfectly on its head, the period would be forever, which makes sense. It's an unstable equilibrium. Not that you ever put it perfectly on its head. By the way, if you wanted to do this as in degrees, we could copy paste. So we just would say theta naught, and Mathematica has this really handy symbol called degree, which is just equal to 180 over pi, but hey, that's kind of handy. So then we can instead run this from 0 to 180, and you get the same plot, but now it's calibrated in degrees. So we can see it goes off to infinity as we go to 180, and the period gets progressively longer. Although at angles really close to 180, you can see that at most the period gets to be maybe triple, but it is for the small angle case. Anyway, cool. Don't save. Quit Mathematica. Alright, so one last topic you remember that I cryptically drew this way back here. Now's my time to steal it. So we'll copy it. And then paste it over here somewhere. That'll do just nicely. Okay, and we're going to go and take a look at these, what we call the Center of Oscillation. Whoa. Doggone it. A-T-I-O-N. There we go. So, remember from the parallel axis theorem, I equals ICM plus ML squared. If we use our radius of gyration notation, so this is MK squared equals MKCM squared plus ML squared. Using that notation, we can cancel the m's. Now, you remember before when we solved for this, and here we're letting the swings be small again, we had that T naught was equal to 2 pi root K squared over GL. So putting in what K squared is, that's going to be 2 pi root KCM squared plus L squared over GL. Now, in this drawing here, what I'm saying is instead of choosing to pivot it about here, there will be some other point on the other side of the CM that I could choose to pivot it about instead and let it swing through a small angle. And the period would be the same. So we call that point O prime the center of oscillation for O. So we'll go ahead and demand that they be equal. So we'll demand TO equal TO prime. So this is 2 pi root KCM squared plus L squared over GL. That'd have to be equal to 2 pi root KCM squared plus L prime squared over GL prime. Okay, we can go on and cancel Palooza here. Cancel, 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 cancel. Just getting rid of what we can. Now if we square both sides and then cross multiply, this is going to become L prime KCM squared plus L prime L squared equals L times KCM squared plus L prime squared. Okay, so let's group the KCM stuff on one side. So that will give me KCM squared times L prime minus L. And I'll put the other stuff on the other side. This will give me L prime squared minus L prime L squared. If I look at that, I realize that I have KCM squared L prime minus L. I can actually pull out an LL prime from both of these, LL prime, and I'm left with L prime minus L. Cancel, cancel. So I get the result that KCM equals LL prime. So my L prime to find my center of oscillation will be equal to KCM squared over L. So for instance, if we go back to our rod, so let's say we were swinging the rod about our point O here, all the way at the end. The CM, of course, is located in the middle, and then this will be our point O prime that we want to find. So here, this is going to be our distance L, which we'll say is A over 2, saying that the whole rod is of length A. And then we want to find our L prime. Well, okay. So KCM squared equals L prime, but we already showed that KCM squared is A squared over 12. L we worked out is A over 2 is L prime. Okay, cancel, 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 cancel. We are left with L equals A over 6. So it turns out that if you put O prime 1/6 of the way, so let's move that dot, shall we? Very carefully. Shoot. I want to just get rid of that dot. No, I can't get rid of that dot. Alright, we'll paint some white over that dot. How's that? Much better. And then we'll move that dot more to where it belongs, right there. So about 1/6 of the way down. Alright, let's put the dot back where it belongs. Alright. So in the next video, we'll continue our exploration of planar motion, taking a look again at angular momentum and going from there.